So, that's the wrong book. Okay, here we go. So, just as another review, we reviewed three kinds of work at this point, three kinds of energy, rather. Maybe even four, I guess you could say. The first kind of energy that we talked about is work, which is the kind of energy that causes movement, right? So work has always got a force involved because it causes movement. Because there's movement involved, there's always involves a distance. We talked about the integral form of this, the calculus version of this, and we did a couple of problems with that, and then we went immediately to the algebraic form of it, because in single dimensions, which is what most situations are that we're dealing with in this class, you don't actually have to use the vector form. You can just do each dimension and add them together, which is fine. So you have this formula, which is actually not necessarily single dimension in force and distance, but it's where the force and the distance can be reduced down because of constancy. So you have constant force over your distance, and the force doesn't change with the distance, which of course is an approximation, but it's a fairly good approximation in many situations. If your force is not constant over the path that you take, you do have to use the integral form. And we're going to go back and do these problems. If we have time today, we'll do the problems in the homework together that involve integrals, since those are a little more challenging, and definitely more challenging for those of you who are just starting calculus. But I think there's only 2 or 3 of them in the whole assignment. But the rest of them are going to involve equations like this that are more formulaic. So that's a good thing for us. And remember, there are a couple of kind of important things to remember about work when you're calculating work. First of all, if you don't move, there's no work, right? If there's no movement, there's no work. Also, if there's no movement in the direction of the force. In other words, if the force and the movement are 90 degrees to each other, then there's no work, right? So those are 2 things. Now here's something else we learned. We did some calculus for the work done to stretch a spring, and that resulted in a formula, once again. A formula that tells us the work done to stretch or compress a spring, which is 1/2 k times the amount stretched, x squared, so 1/2 kx squared. But also you can calculate how much energy is stored in the spring, because when you do work to compress a spring or stretch a spring, the energy that you exerted, the energy that you used doing that work, is actually stored in the spring. So that's what we call the potential energy in the spring, or the spring potential energy. So we learned a little bit about potential energy in the first section as well. And then in the second section, we went ahead and learned about kinetic energy. Now this equation, kinetic energy equals 1/2 mv squared, where v is your speed essentially in any given direction. This is a formula that is derived from calculus. We don't really get into the calculus version of this in this class much, mostly because we don't need to, and gets a little bit crazy. But this is the general format to calculate the kinetic energy of a particle. And if you have many particles, of course, you can add them all up by calculating the kinetic energy of each one. If you want to, there are other things you can do with this equation. You can recognize that v is that the speed of a particle is also related to its momentum, as long as you're just talking about the magnitude of the momentum. And so the momentum being m times v, you get the kinetic energy equals the momentum squared over 2m. So this actually gives us a direct relationship between momentum and kinetic energy. And why is that important? Because it's important historically, because momentum and kinetic energy were always confused with each other. Nobody could really tell which one was which and why. And there was a lot of argument about that over the years. And it wasn't really until the French noblewoman I was telling you about came along and cleared it up for everybody back in the 1700s that it was figured out. But anyway, historically, that's quite important. So you have some equations for kinetic energy, and we're going to calculate kinetic energies of different objects. Remember that just like work, kinetic energy is not a vector; it's a scalar. But work can be negative. If you do negative work on an object, then you're taking energy away from the object. If you do positive work on an object, then you're putting energy into the object. Whereas kinetic energy can never be negative. Why can kinetic energy never be negative? Looking at this formula. Because the only thing in there that can possibly be negative is the speed, which is squared, right? And even speed is not really considered negative usually. It's usually just the speed, right? So there's nothing in this formula that's negative. Even in the calculus version, there's nothing in it that can be negative because the velocity in that point, in that case, would be squared. So, yeah, that's really what it comes down to, is that you cannot have a negative kinetic energy. Kinetic energies are always positive. No ifs, ands, or buts about it. So that's what we learned about kinetic energy. You can also deal with relative kinetic energies. Here they do an example of this we didn't really talk about in the last section, where you still have the classic relativity equations. If you're walking in the same direction as the frame of reference that you're in, for example, then you have to add those velocities together to get the total kinetic energy of the person who's walking on the train. You need the velocity of the train plus the velocity of the person relative to the train, right? But if the person is walking in the opposite direction of the train, of course, their overall kinetic energy is actually going to be less than it would be if they were just standing on the train, and so on and so forth. And those things can be important when you're dealing with moving reference frames, for sure. But now we get into what we call the work energy theorem. Hold on a second, I'm looking for something that I'm not seeing. We did learn about gravitational potential energy, didn't we? Did we? Trying to figure out where they put that. I think it's here in the first section. The work done against gravity, I think they call it. Yeah, right here. So in this case, this is the other one that I wanted to mention, is the work done against gravity. When you say the work done against gravity, that's always movement straight up where gravity is pointing straight down, right? And the work done against gravity is equal to mg times the change in the height. And they throw a negative sign in front because the work that you do against gravity is always in the opposite direction of gravity, right? But this is also equal to the potential energy. This mg times h, if you take the negative sign off the front, is also equal to what we call the potential energy that you put into an object when you lift it up higher than it was. Or you can take potential energy out of it by lowering it down from where it was, right? But this potential energy here is actually very interesting in that it depends on where you're calling your 0 point. Let me see if I can find it. So, if we're considering the floor in this classroom our 0 height, and we go 10 feet above the floor or 3 meters above the floor or whatever, then we increase our potential energy by the mass of the object times that 3 meters, right? But What if we consider our potential energy to be the bottom floor of the building and we raise it up 3 meters above this floor? Well, then we have to add on the other 3 meters, or probably 4 or 5 meters between floors, right? But the difference in potential energy is still the same. We still went from this floor up 3 meters, right? So the potential energy is never absolute. The potential energy is always a difference of potential energy from one point to another point. And what that, how that difference shows up in the math depends on how you, where you define your 0 point. For any given problem that you have, you should always define the same 0 point for that problem. But in the end, the change in potential energy will always be the same, because the answer will always be the same, even though the numbers look different when you're calculating it. When the numbers come out, it'll always be the same. It's like 3 minus 0 equals 3, and 15 minus 12 still equals 3, right? That's the difference, because you've defined your 0 point or your starting point in different places. So thus far then, if we talk about section 1 and section 2 here, we have learned about work, which is the type of energy that causes things to move. You can use work to move an object from point A to point B. You can use work to stretch a spring or compress a spring, in which case you put energy into the spring. And you can use work to lift an object or to lower an object in a gravitational field, in which case you're changing the amount of potential energy that object has in the gravitational field. When you lift it higher, you increase its potential to move, and when you bring it lower, you decrease its potential to move. Kinetic energy, of course, is the energy of movement. And then we move on to movement itself actually has its own energy to it. Then we move on to the work energy theorem. And what is that? Well, what the work energy theorem is it's an equation that essentially recognizes that all energies are the same thing. They're all energy. And energy is not something that can be easily destroyed or created. Can it be destroyed and created? Yes, it can be. It's not something that they talk about much in science, because physicists are the only ones who can do it. But energy can be created and destroyed. It's just very difficult to do. We thank Albert Einstein for that once again. But in most of the situations that we're going to deal with, and all of the situations we're going to deal with in this semester, we're going to assume that energy cannot be created or destroyed. That means it has to go from one type of energy to another type of energy. It just has to move from one place to another, transfer around, trade back and forth, and we have to be able to account for it. So this is kind of like accounting. It's like physics accounting, right? The work energy theorem. So how do we put this theorem together? Well, it is a physics thing, and it starts with calculating the amount of work done on a particle, the net amount or the total amount of work done. And in calculus, when you're doing something like this, you need to start with a derivative, which is a small piece of that work, and then you need to use an integral to add up all those different pieces of work. And then once you've done that, then you have the total amount of work done on a particle, and you should know it's the total energy that is gained from that work. So here is that dW, that little piece of work, that derivative of work. Well, work is a mass times work is a force times a distance, and the force here has some derivative to it, has some change in it. So whenever you take a derivative of some kind of quantity, it will be equal to the derivative of its constituents, which in this case are force, mass times acceleration. Acceleration is a derivative, so we write it as a derivative, times distance, and in this case we break the distance down into a derivative of our distance vector, r. And then there's the dot product in between them again. Then we can actually simplify this a little bit by splitting up this derivative, this time derivative here. Now this is something that mathematicians hate physicists for. Because we just say, well, it's kind of like a fraction. Just move the dumb dt over here, and leave the dV by itself. It's just like, I mean, you can do this when you're doing just regular arithmetic. And it turns out you can do it when you're doing derivatives as well, but you can only do it when the derivatives are what we call separable, when the functions are what we call separable. And in physics, they're pretty much always separable, so we don't worry about it. In mathematics, they get really uptight about it because technically speaking, you can't do this, but in mathematics, the mathematics for that kind of thing don't correspond to anything in the real world, so we don't care about them. If the mathematics don't mean something in the real world, physicists just ignore the mathematics. So that's what we're doing here. We're ignoring those mathematics because it doesn't mean anything in the real world. So anyway, the point is that we can just kind of change that time derivative over to the r vector here, the derivative of the r vector. And when you take the derivative of the r vector in time, you actually get the derivative of the velocity vector. So this whole thing here, this work thing, becomes mass times velocity times the derivative of the velocity. And if you take the integral of that, of both sides here, when you take the integral of a complete derivative here, you get, you just get whatever the derivative was. So in this case, we just get the work done from A to B. And then taking the integral of the dot product between the mass times the velocity times the derivative of the velocity, we just get this dot product, mvx dvx plus mvy dvy. Remember, the dot product splits the vectors up into their individual components in each dimension and multiplies them and adds them together. So this is the dot product between these two vectors. Now it's inside of an integral. And when we go ahead and do this, it's actually fairly simple. It's simple calculus. The mass the mass here is a constant, so it comes out. We're taking the integral of v with respect to v, and so it just becomes v squared in each case. And so when we do this, we get 1/2 mv squared. Well, 1/2 mv squared is the kinetic energy. We already knew that. And what this is telling us is that the net work in any situation is equal to the difference in kinetic energy. So if you add up all the forces times all the distances in a situation, you will get a change in kinetic energy, and that change in kinetic energy is equal to the sum of those net forces. And this is what we call the work energy theorem. So in the end, it's really quite simple. It's not you don't have to do any of this calculus or anything else. We just have to calculate the difference in kinetic energies, and that will tell us the net work done. Or if we know the net work and we know one of the kinetic energies, we can calculate one of the kinetic energies, right? The other kinetic energy. So that's exactly what we're going to do here in these coming examples. Here they actually go through a couple of different situations with this. So remember, there are different kinds of work. We can do work against gravity, so we can do work up and down. We can do work that's just going to increase the speed of something, change its kinetic energy sideways, and we can do a combination of those. We can do work that goes up an incline, like up a hill or down a hill or something like this. And so, but we can also do work with friction. Remember that friction does work whenever we push something. If there's friction, it will push in the opposite direction and do work that takes energy out of the system, which would be negative work on the system, right? So there's lots of different kinds of work that can be included in this net work on the left side. Lots of different kinds of forces over distances. On the kinetic energies on this side would include all the kinetic energies of the system, or the kinetic energy of the entire system. That's a good way to say that. So what happens if we're going up or down a hill? If we're going up or down a hill, then all of a sudden our so in this case, this is an object sliding down a frictionless plane. And when you have an object sliding down a frictionless plane, you actually get a change in potential energy that has an angle in it. In this case, the sine of this angle. And then you have a difference in positions along the edge, and you have 2 times g ends up in there, and you have velocities squared and everything else. And this actually starts to look like this is actually a kinematic equation, right? This is actually a kinematic equation, but it actually can be derived from this equation that we just derived up here. This equation up here has initial and final velocity squared. This one down here has initial and final velocity squared. So we've already done kinematics, and we've already figured them out from other things, but now we're starting to realize that, hey, we can figure them out from kinetic energies as well. The kinematic equations were not just guessed at, they were actually derived from the mathematical theories of the scientists of the day. So let's say that all the work that we're doing is just gravitational work. We're just lifting it up or lowering it down. Well, if that's the case, we already know that it's the change in height times m times g is equal to the work done by gravity. Right? Well, and if that is the case and it changes speed, then the work done against gravity has to equal the change in kinetic energy. So then that makes this equation true, right? And if we divide by m on both sides, we get this equation up here almost. It's not exactly this equation, but it's pretty close. If you take this difference in the position along a ramp, this, which is what this s is, and multiply by the sine theta angle of the ramp, then you actually do get this right here. This equation comes out. The m's are dropped off, and you get g times the difference in height times 1/2 times the difference in velocity. Or in this case, 2g on the left side, on one side, and change in velocity on the right side. So it all kind of comes together here. All these kinematic equations we learned before, it's combined with Newton's laws, and then combined with energy, the ideas of energy, bring us back around to the same equations we had in kinematics, which is a very important thing to realize, because that's telling us that our equations, our model, is what do they call that? They call it self-consistent. It's consistent with itself, right? If we'd solved for those and we got another equation that contradicted our kinematic equations, then we'd be worried. Then we'd have something to fix, but we don't, so we're good. So how are we going to use this work energy theorem? It's really quite simple. When you have a situation, whatever physical situation it is, in this case it's this loop-to-loop thing. You have a particle, whatever it is, that's going to slide down in gravity along this path, go through this loop-to-loop, and then come out the bottom. At any given situation, at any point in the problem, the energies can be found and added up. You find all the energies at any given point and add them all together. And then you find the energies at any other point and add them together. Now, some of those energies may have unknowns in them. You may not know, for example, the speed of the particle at the top of the loop. So you may not know its kinetic energy at the top of the loop. You may not know its height at the beginning. So it's a variable, right? If that is the case, then you just write out the energies with variables. So if you're writing out the potential energy at the beginning with variables, it's just the mass of the particle times the g constant, the gravitational constant, times the height. And if you don't know the height, you just put in h, right? In this case, if you don't know the velocity at the top of the loop, then you write the kinetic energy as 1/2 times the mass of the object times the variable v squared, right? Now, I actually recommend that you don't write any numbers into equations anyway until you've solved the problem, because it makes it easier to look for mistakes. But in the very least, you need to realize that you can still write down energies even if you don't know the actual number for the energy. You can write it down as a formula, and then you can put it into this equation. So once you've figured out the energies at two different points in the system, you need to identify which variable in those energies is the one you're looking for, the one that you want to know. And then you need to plug those energies into the work energy theorem. What is the work energy theorem again? It's this theorem up here that says the net work is equal to the difference in the kinetic energies. But it can be modified because the net work can also be equal to the difference in potential energies, and gravitational potential energy, right? Or spring potential energy. So, but you essentially add up all your works, the different kinds of work that are being done, put them on the left side, and then on the right side, you say the difference in kinetic energy. So you need the kinetic energy at one point minus the kinetic energy at another point. or the kinetic energy at your ending point, very specifically, minus your kinetic energy at your beginning point. And they can include variables. So you plug those things into that equation as your second step. The third step that you need to take is you need to solve that equation for the thing that you want to know. And then you plug in numbers and get a number, get a value out, right? Evaluate. So let's do this example with the loop-to-loop. At the beginning of the loop-to-loop, which is at point 1, we have a velocity of 0. Okay? They tell us the velocity 1 is 0. That means our kinetic energy at the top there is what? Our velocity is 0. What's our kinetic energy? Also 0, right? So we know our kinetic energy right here. We also are going to assume that the bottom of the loop here is going to be our 0 point for measuring heights, if we want to calculate potential energy. So we'll just call the bottom here 0, and we'll call the top y1. So y1 is our highest height here, or it's one of our heights. I don't really know if it's higher than the other one, but it's one of our heights here at point 1. And then we have y2, which is twice the radius of the circle, at the top of the circle. Here they're saying the gravitational work is the only work done over the displacement that's not 0. In other words, we're not going to have any friction. We're just going to have gravity is the only thing that's going to be causing this ball or this point to move. Okay? So there's the only kind of work on the left side of the work energy equation is going to be gravitational work against gravity, which of course is equal to negative times m times g times the height change, right? Negative times m times g times the height change. So that's what they write in there, negative m times g times the height change, y2 minus y1. Why y2 minus y1? Because y2 is where it ends, y1 is where it begins. You take the ending position in height minus the beginning position in height. And that is going to be equal to our change in kinetic energy. We already said that our initial kinetic energy is 0, and the change in kinetic energy is your final kinetic energy minus your initial. Our initial was 0, so this left side of the equation is just equal to 1/2 mv2 squared, where v2 is the final velocity, or final magnitude of velocity. So what do we want to know here? We want to know how high from the bottom of the loop must the car be placed to start from rest on the approaching section of track and go all the way around the loop. So let's think about this. What speed do we need to achieve at the top of that loop if we're going to get all the way around? What is the absolute minimum speed we need to attain? Or the minimum, well, I guess, what do we need to accomplish when we get to the top of that thing for it to go all the way around? What's that? Yeah, it needs to, I mean, at the very least, like the tipping point is when it goes up to the top of the loop and it stops, right? But we need just a little bit more than that, right? And this is not a track, this is not like a train track either. Oh, so we actually have a different condition we need to maintain. I'd forgotten that this is not like a roller coaster that's connected to its track. This is like a car. Does it say that it's a car? Oh, it does say it's a toy car. So this is a toy car that is on like one of these toy track things, these little plastic tracks. It's not connected to the track. So there's a different condition we need to meet. At the top of the loop, what's pulling on the car? Gravity is pulling down on the car with mg, right? It needs to have a normal force from the track that is, well, it needs to have what we call kind of a fake, that centrifugal force into the track that is at least equal to mg to stay on the track, right? So the normal force from the track onto the car actually needs to be equal to mg in order for it to stay on the track, at least. So we need a, let's see. So we have a, what they're showing here is here they have the equation for this is the equation for the work energy theorem, right? And here they're going to show, this is Newton's second law, acceleration at the top has to equal the force over the mass. The force is there are going to be two forces. There's going to be mg and there's going to be the normal force, and divide that by m for Newton's second law to solve for the acceleration. The acceleration at the top also has to equal v squared over r, v2 squared over r, because that is how we define the acceleration of an object going around in a circle. So why do we do all this? We do all this because we need to calculate what the normal force has to be in order for this to happen. So it turns out if we solve the normal force in this situation, we get this actually. We get, it has to be equal to mg plus 2m minus mg plus 2mg y1 minus 2r over r. Right? That actually has to be greater than 0 for this to happen. And what they're saying, what this is saying here, is the saying that the weight of the car plus the normal force has to equal 0. They have to cancel out. That's all this is saying. But there's a couple of things involved here because of the velocity going around, the centrifugal force, so to speak, right? So this formula tells us what the normal force has to be. Excuse me. And if you solve this one, actually, if you solve this inequality to figure out what r has to be, or sorry, what y1 has to be, you'll find that y1 has to be 5 halves times r, so it has to be a little bit bigger than the circle. Half a radius bigger than the circle. So here's another situation that I think is a little more clear on what we have to do. In that last one, they actually kind of took a departure from the energy equation and went into the Newton's law thing down here, which I think could have been done without really using this. The only way that they really used this was when they got down to, I don't think they used it at all, actually. So that's kind of annoying. Yeah, I'm not sure this problem actually even, I don't think we even needed the energy to do this problem, but we used it anyway. They weren't able to determine the answer from the energy, so they went to Newton's second law, which was exactly what you weren't supposed to do. Could have done it with the energy, I suppose. Anyway, here we're going to use just the energies now. So here we have a bullet that's flying through the air at 335 meters per second, which is just faster than the speed of sound. And it's going to hit this block of wood, right? It has a mass of 40 grains, which is 2.6 grams for the bullet. And the speed is 1,000 feet per second, which is 335 meters per second. It can penetrate 8 1-inch pine boards with a thickness of 0.75 inches. So they're called 1-inch boards, but they're only 3/4 of an inch thick. And they want to know is the average stopping force exerted by the wood. How much force is stopping the bullet? Well, force stopping something is like work, right? So we have some kinetic energy to start with. Then at the end, the energy of the bullet is going to stop. There's going to be no kinetic energy in the bullet, right? And what kind of work was required to do that stopping, to make that stopping happen? Well, net work equals change in kinetic energy. The net work is equal to the negative, the force, the average force times the stopping distance. It's force times distance again. And why negative is because the work is in the opposite direction of the motion. And that's going to be equal to the negative of the change of kinetic energy. So what is the change in kinetic energy? Well, the initial kinetic energy is this right here, and we take the final kinetic energy, which is 0, and subtract this from it, and we get that change in kinetic energy. It ends up being negative this, but since there's a negative in front of this anyway, they just strike the negatives here. So you end up with this kinetic energy on top divided by this distance that it goes through on the bottom. Point, oh sorry, 960 newtons. Ugh. Now, can you use Newton's laws to do these problems? Yes, you can. However, when you use Newton's laws to do these problems and kinematics to do these problems, you often will use more equations, especially when you get into more complex situations. For example, the football player throwing the football down the field and the football follows a trajectory that goes up and then comes back down again. That becomes a fairly complex problem using Newton's laws in kinematics. With kinematics, it usually involves two-dimensional kinematics, which involves at least two equations, two unknowns, solving all this stuff, a big messy thing. With kinetic energy, it doesn't. With kinetic energy, it's just how fast was the ball going at the beginning? How fast was it going at the end? There was a change there in kinetic energy. That change in kinetic energy has to show up somewhere else in the equation, either as a change in potential energy or some work being done by friction or something else. And that's where it comes out. So that is the work energy equation. Now the last part of this is power. What is power? Power is, in essence, how much energy is being used up every second. It's the energy use. It's like the velocity of energy use, right? So the definition is the change in work over the change in time, or you can think of it as change in energy over change in time, however you want to. The definition as far as calculus is concerned is dw dt, or the time derivative of the work, and that's fine. If it's the time derivative of the work, then of course you can rearrange this equation so that you have dw equals p dt, and then take the integral of both sides and you can get the work equals the integral of the power in time. So if somebody tells you what the power is, you can take the time integral of it and calculate the work. For the most part, we're going to use the formula for this instead of the calculus, instead of doing the calculus. So here we have an 80-kilogram army trainee doing pull-ups. It takes 8.8 seconds to raise the body from the lower position to where the chin is above the bar. How much power do the trainee's muscles apply, moving his body from the lower position to where the chin is above the bar? Right, okay. Do they say what the distance is? I don't think they say. Oh, so they just assume, right here they assume that it's going to move about 2 feet. So it's about 60 centimeters, 0.6 meters, and that's fine. But in this case, the power is equal to the amount of work done, or the change in the work, divided by the time. So the work is m times g times the change in height for this, because they're doing work against gravity, right? So mg times change in y over t, and they plug in all their numbers and they get 529 watts. 529 watts, you go into your house and you have 50 watt light bulbs, 100 watt light bulbs. That means that those light bulbs are using about 1/5 the amount of energy as somebody doing pull-ups every second. Which really gives you the thought that there's quite a bit of energy in our body. We use a lot of energy to do things in our body. There's another example where we're going up a hill. Mass of the car, velocity of the car, we have a 15% grade. We have no change in kinetic energy because it's constant velocity, right? We want to know right here how much power the automobile engine expend to move a 1,200 pound car up a 15% grade at 90 kilometers per hour. Well, the work being done to change the speed of the car is 0, right? Because the speed of the car is not changing. However, there is work being done to lift the car up to a different height. So there's gravitational work being done. You always have to think what kinds of work are being done. Is any of the work changing the speed of the system? In this case, the speed of the system is constant, so there's no work doing the changing of the speed of the system. Is there any work being done that is changing the height of the system? In this case, yes, it's going up the hill. So there's gravitational work being done, that's MGH, right? So they go ahead and they calculate that, MGH. But the MGH is equal to, they use V times the sine of the inverse tangent of the point 15, which gives them, the V sine tangent 15 gives them the change in height over time. So that's their change in height over time. And so that's going to actually give them power. It turns out to give them mg times power. So they solve for the power and they get 58 kilowatts of energy to go up that hill. Now that's assuming there's no friction. If there was friction, we'd have to calculate another work being done by friction, and we'd have to tack that onto the other work. This much, essentially this tells you how much energy you're losing every second trying to lift this car up the hill. If there was friction, it would tell you how much energy per section the friction, how much energy per second the friction is removing from the car as it goes up the hill, and so on. And that finishes up the chapter. Now, we do have homework problems to work on. We've got a few minutes today. Does anybody have a particular homework problem they want to see? Problem 1? Okay. Well, problem 1 is a good one to get done because that's a tough one. I would skip the first 3 and start working on 4, honestly, and then come back to the first 3 later, because the first 3 are the calculus ones. Number 4? Okay. Well, number 4 is very similar to the one done in the book with the lawnmower, except instead of pushing the lawnmower, we're pulling the wagon, right? So we're pulling with a force of 58 newtons, angle of 40 degrees, and we go a distance of 20 meters. Work is equal to force times distance times the cosine of the angle between the force and the distance. So that's what you do. You take the cosine of 40 degrees, multiply it by the 58 newtons, multiply it by the 20 meters, and you will get the amount of work done on the wagon by the boy. By the way, if any of you would like some tomatoes to take home and eat, or watermelon, I've got some tomatoes and watermelon in the back of my truck outside. If you go out the back door and go left of the planter, my truck is there with its bed open, and there's a sign in the back that says free produce. This door. Yeah, so go out the north side. Got some. Those are from the research farm. We're sharing produce with the community from the research farm. So. Any others? That's what a lot of these problems are going to be used, making use of that, making use of the equations, the energy conservation equation. And then if you get towards numbers, get towards number 15 and beyond, we start to use friction to do work, and then 6, 17, 18, 19, those are power problems, where you calculate the amount of work done and then divide it by the time that it was done in. Any other questions? We're good to go? All right. Have a great day. See you tomorrow for a lab, and then we will do some more homework questions on Friday.